Yes. Okay. Hello. Okay. This is the third in the sequence with David Chach, a star student from BU. I have to advertise the fact that we contribute to the scientific community, and it's a pleasure to have him here. Thanks.
This is the third and final part of my lectures on lattice supersymmetric field theories. And just as a reminder, what we've been doing so far is really a deep dive into lattice formulation of N=4 supersymmetric Yang-Mills, showing some of the challenges that have had to be overcome to realize that system in the discrete spacetime of the lattice, and then highlighting some of the opportunities that are opened up by overcoming those challenges. So what we did yesterday was finish writing down formally how this system is set up on the A4 star lattice with 5 symmetric basis vectors in 4-dimensional spacetime, and doing some bit of RG analysis and lattice perturbation theory to get some nice analytic results for that formal setup, showing how when we are able to preserve this single supersymmetry out of the full 16 in discrete spacetime, then the situation becomes much nicer, and recovering the continuum target theory of interest requires only tuning this one free parameter rather than the roughly 10 or so that we would get with a more straightforward, naive discretization. And then that simplification is what allows these lattice analyses of N=4 super Yang-Mills to become practical to do with the computers that exist today. But practical does not mean easy necessarily. And the remainder of yesterday was spent looking at how, in practice, we have to deform or modify this lattice system in order to make these numerical calculations function and be something that we can actually do on a physical computer to get numerical non-perturbative predictions for this system. So today we will wrap up that look at numerical calculations in 4-dimensional N=4 super Yang-Mills, just looking at one example, and then more quickly go through all of the remaining pieces on this outline, looking at lower dimensional systems, minimal super Yang-Mills in 4 dimensions, which is simpler for a different reason. And then that connects to some of the ongoing or even future work that needs to be addressed, in particular looking at the complications that arise going from super Yang-Mills to super QCD, and then the sign problems that we will get to today and define what that means. So are there any questions about what we've done up till now before I charge ahead with the remainder of that N=4 lattice application? Not seeing any, we'll just pick up roughly where we left off, the reminder that the lattice action that we ended up having to write down in order to control all of the things that can go wrong in a numerical calculation ends up a bit complicated, more complicated at least than the nice continuum theory that we started off with and that we recover by going through this procedure. There is a parallel code for high performance computing that is available, that is being actively developed both to improve its performance and add some new applications, including super QCD, to this basis. And what we looked at yesterday in order to figure out why all of these deformations and other terms have to be present in this lattice action in some way, shape, or form, whether that's an explicit supersymmetry breaking potential or a twisted boundary condition or a modification of the moduli equations. We were looking at things like violations of word identities, the density of monopole world lines, the Malda-Sena loop that is the analog of the Polyakov loop with these complexified gauge links that include both the gauge bosons and the scalars. And all of those are interesting to look at as diagnostics to check that we are obtaining the theory that we actually want, but they're not so interesting in terms of physics. So among the more physically oriented calculations that have been done or are underway in 40 N=4 super Yang-Mills on the lattice, I'm going to spend a few minutes just to go through one of those, looking at the static potential, and in particular, the coefficient of the Coulomb term in the static potential. So as a either reminder or brief introduction, what the static potential is looking at is the behavior, the interaction of static probes, so infinitely heavy test charges that we put into the system, we allow to evolve in time. And that is described on the lattice by these Wilson loops that have half of their legs oriented in that time direction, and then are separated by some spatial distance on a slice of constant time in the lattice volume. With the A4 star lattice, figuring out all of the possible lattice paths and the corresponding spatial distances on those time slices becomes fairly complicated. So most of the static potential work that I've been doing uses an old trick from QCD. I'll switch to the handheld mic while the battery in the clip-on mic is replaced. So I was saying that there's an old trick from lattice QCD, which is to fix the Coulomb gauge. All of the propagating information gets shifted away from the spatial links into the temporal links. So just by taking the correlator of two segments, products of gauge links along this direction in time, separated by these distances coming from the A4 star lattice, we get data that looks like that as a function. So the static potential is a function of R coming from the exponential decay of those Wilson loops with the time extent of the extent of their length in the time direction.
Excuse me. Yeah.
Thanks. So we are back on this mic. So fitting that exponential decay for every fixed R as a function of t gives us each of these data points coming from the same set of gauge field configurations, where the gauge includes the scalars and all the rest, which we can then fit here to the Coulomb potential to determine the Coulomb coefficient. Now, I should say that this is.
Are the error bars statistical or are they?
Those are all just statistical error bars on there. And I should also mention that I was alluding to this because all of these points are coming from the same set of field configurations. They are extremely highly correlated. So it looks like there's an impressive amount of data with tons of data points up around these larger distances, but really it's all different ways of slicing the same underlying information that we have in the system. So just statistical errors on those points. And actually, I should not, this looks like a Coulomb potential 1 over R, but we don't need to assume that. What we can do is fit to a confining potential, the sort of thing we would see in lattice QCD, where there is a string tension that rises, that it parameterizes the linear rise in the potential at long distances in QCD that corresponds to confinement. We can measure that string tension and show that it is 0 for a variety of lattice volumes and gauge groups. Okay, it's approximately 0. There's some interesting deviations toward negative values that are actually easy to understand if we go back to the picture that we have and realize that our finite lattice volume is cutting off the distance that we were able to go out. So at these large distances, things are more or less constant within error bars. And these fits to this confining potential are bringing in a slightly negative string tension just to flatten out the potential at the largest distances that are able to obtain, which when we increase the lattice volume and are able to see that things keep rising rather than ending up flat or just stopping at that point, we can see by the different colors here with these square boxes that this lattice volume increases from 8 cubed times 24 to 12 cubed times 24 to 16 cubed times 24. This artifact in the string tension goes away and it approaches 0 fairly steadily. One interesting aspect of these results that I want to highlight as a sort of generic lattice tool that can be in the toolbox has to do with what is being plotted on the horizontal axis for the Coulomb potential here, what I've called an R sub I, which is denoting an improved radius from a perturbative improvement of this static potential analysis. So this is an idea that was introduced in lattice QCD in 1982 by Claudio Rebi and Lang, whose first name I forget. And this is related to discretization artifacts that are visible if we don't do this. So if we just have standard R's, the scalar distances that would correspond to the direct displacements of the spatial slices, the time slices of the A4 star lattice, at the short distances separated by one lattice spacing or off on the short diagonals, we are able to see fairly large fluctuations around that sort of smooth 1/r behavior of the Coulomb potential. So here on the right, comparing 2, 3, and 4 color theories with everything else fixed. Sorry, that's the left. And then the plot on the right is essentially unwinding that Coulomb potential dependence to highlight the fluctuations of the data points around the dotted lines, which become that dotted line at -1, just subtracting the A and multiplying by the Coulomb coefficient, and then scaling by R to get a constant. So at these short distances, there are big fluctuations up and down that are probably doing a lot to determine what the actual Coulomb coefficient is when fitting to this Coulomb potential. That is, that region of small r is where these fits are most sensitive to what we want to get out. And we should be worried about these fairly large fluctuations above and below that smooth behavior of the Coulomb potential, which we can expect to be coming from the system being able to see the fact that it's living in discretized space-time. It has this lattice spacing, and that's what we don't want to be sensitive to when we compare to the continuum theory and continuous space and time. So the trick from 1982 and refined since then is to take that static potential from fits to the exponential decay of Wilson loops and say that for a given spatial displacement, it is associated not with the naive displacement on the A4 star lattice, but rather with the effective distance that the gluon propagator would see in the system, which can be computed in lattice perturbation theory using the same tree-level propagator that we looked at when talking about the beta function in lattice perturbation theory yesterday. So this work with Anosh et al. From about 10 years ago. So if we recall that there's a nice relationship in the Fourier transform of the gluon propagator in the continuum in Feynman gauge, we just take this relation between some distance scale and the integral over momenta, the Fourier transform of now, instead of the continuum propagator, we put in the tree level lattice propagator that knows about the discrete structure of space-time and brings in these trigonometric functions of sine squared of the momenta rather than just 1/k squared. Then for each 4-vector R sub nu in the A4 star lattice, that corresponds to the improved distance R sub I, which is what gets plotted then on the horizontal axis. So this is the same set of data as shown here to illustrate these fluctuations with a naive distance scale. We've just changed our definition of what the distance is to account for the discretization of space-time. And this plot with these big fluctuations ends up like so, where now things are much smoother at those short distances. Some of the discretization artifacts have been accounted for by this way of working with things, and we can have more confidence in the Coulomb coefficient that we get out from fits to these data in the end. So this is the at least preliminary results that we have for those same sets of theories with 2, 3, or 4 colors and various different lattice volumes. Looks like there's a question.
Can you go back a second?
I can.
So the improved R, so you measured the R directly from the calculation, right? And then you pass it through this filter and then you do the plot, right?
Yeah, so the 4 vector R in the A4 star lattice is input to this calculation. So that appears in the numerator of this
Okay.
integral.
So for short distances, does it move it in or out, or it moves
Moves
some
out.
in?
Generally.
Okay.
And in particular, that second point that was very high before, that's the one from the shortest diagonal in the A4 star lattice.
Right.
And that has about the largest relative effect from this calculation. I should say this 4 integral we evaluate numerically using the Vegas algorithm. So it's a Monte Carlo sampling just of a 4D integral in order to define the horizontal axis here. And part of the reason, or the main reason that this second point is now lining up better with the curve is that it's been shifted out to larger distances where the Coulomb potential is
Right.
has risen up. So it's now,
So there's a typo in that formula, right? There's no I, right?
oh yeah, sorry. It's an E to the I, RK, and I expand
okay.
E, so that is a typo, yeah.
Okay, thank you.
You can have either exponential IRK or expand that into cosine plus I sine. And because the sign is odd in a symmetric domain, the sign cancels out. So yeah, no I there. That is just a typo. Good, so we have, so that so-called tree level improvement of the static potential gives us these Coulomb coefficients from fitting to the Coulomb potential, the data that we have. And the dotted line here is the perturbative prediction at tree level, so just linear in the 't Hooft coupling. And if we were able to get out to much stronger couplings and possibly larger N, we would hope to approach the regime where the holographic gauge gravity duality brings in its own prediction, or how this Coulomb coefficient behaves as a function of the 't Hooft coupling. There's a famous square root lambda dependence in that regime, which was one of the first predictions to come out of ADS CFT duality, I think in 98, just a few months after it had been introduced. So our results are nowhere near that. It's reassuring that we can reproduce perturbation theory or show consistency with perturbation theory at weak coupling. So that's a good check that we are, in fact, calculating the correct theory. And the push to stronger coupling is, at least with this action, where issues with the sign problem come up. So I think that's all I have to say about this, and can take the next.
Usually, if you pare a square root, you get a minus sign on the first term. So this looks like it's going up. Is that?
So yeah, you're asking about, are those points?
Yeah, they should. I would expect them to be below the line. So.
So would I, yeah. Yeah,
Okay.
so here, things get harder as the coupling gets stronger. And that's going to show up in the future challenges section of the talk, because around that coupling of 2.5 or even 2 is where we start to see issues with the sign problem with this particular action. And that, this is not a significant shift given the error bars that we have there. So I wouldn't read physics into whether it's above or below that line. The short answer is it's not really showing anything about holography yet. We want to do that, and that's going to be a challenge for the future. But for now, I'm going to declare victory with this deep dive into the N=4 super Yang mills in 4 dimensions, have a few more topics that we'll go through much more superficially and more quickly, just flashing some highlights and discussing some of the issues that are encountered without going into such level of detail. But before I move on to those different topics, are there any questions, any further questions about the 4D N=4 lattice super Yang mills? So the next topic will be lower dimensions. I'm actually going to start by looking at naive dimensional reductions of this 16 supercharged theory going into lower dimensions. That's going to be my focus, though there are lots of things that you can do with various different theories in these lower dimensions, even going beyond dimensional reductions of super Yang-Mills and looking at things like Wess-Zumino models and systems without gauge invariance, as well as super QCD that we'll get to in a bit, hopefully. And really, I would say most of the work of the lattice supersymmetry community over the past decade has been focused on these lower dimensional systems just because they turn out to be a lot easier. So in these lectures, I've really started with the hardest case, and now everything else will look easy in comparison. But if we want to get papers published, then we often go the other way around, start with the low-hanging fruit and focus on that and only build up to that harder case of 4 dimensions later on. So some of the simplifications are related just to the fact that in smaller numbers of dimensions, the numbers of degrees of freedom in your lattice calculation scale more slowly as you go out to larger lattice volumes. So you have an L to the D with D of 2 or 3 rather than 4. And maybe even more significant is the fact that each of these degrees of freedom has, well, fewer interactions with the other degrees of freedom. Each lattice site has a fewer number of nearest neighbors for it to interact with. So when you have to go through and compute the effects of all those interactions, there's a lot less work to do. These systems are also not super conformal, at least not in the way that n equals 4 is. They have, in the super Yang-Mills case, dimensionful 't Hooft couplings. In some cases, they are super renormalizable, and rather than fine-tuning parameters in numerical calculations, you can actually do a simple one-loop calculation in lattice perturbation theory to figure out what the appropriate counterterm is to recover the continuum limit. I won't go into any more details about that. I also, when looking at the time and the pace that I've been setting with these lectures, decided to save all of my ongoing work in 3 dimensions for my research talk next Monday. And what I'll do here is just flash some highlights of some older work I did in 2 dimensions, as well as some of the other possibilities in 2 dimensions, and even fewer highlights of one-dimensional quantum mechanical lattice systems, because that is such a big topic with so much work that Georg Bergner is going to give a whole set of 3 lectures just on that topic next week, looking at matrix models and their relation to holography and numerical simulations. So the set of results I'm going to go through in this 2-dimensional case is looking at the thermodynamics, the phase diagram of 16 supercharged super Yang-Mills dimensionally reduced to 2 dimensions from 4. So we take the 4-dimensional theory, compactify 2 of the spatial dimensions, and end up with just a 2 torus with some spatial length r sub L and some temporal length r sub beta. And there are now 4 scalar supersymmetries that are exactly preserved by this system. Thanks to that A4 star lattice structure, this torus actually ends up being skewed, which is interesting, but maybe not so important to get into now. I'll also mention that in the numerical calculations we do, we also just use the 4-dimensional code and implement this naive dimensional reduction by setting 2 of the lengths in the code, 2 of the lattice lengths to 1, a single link that loops around itself. There's already a question from Rich, so.
Yeah, what do you mean by skewed? I'm
So
interested in skewing.
yeah, but I don't have a picture of it.
Maybe you can just say.
Yeah. So
It's rotating before it goes back together.
this,
Okay, good.
Yeah.
Sorry.
in the tau plane, we end up, depending on the aspect ratio of this torus, the relative spatial length versus that temporal length, we end up with different taus. So
Okay, very good. I'm sorry. I must have.
real part of tau is 0 corresponds to a
I
rectangular.
blanked out, but a shameless ad. Tomorrow, I will actually solve points.
The interesting thing about this behavior. So this is for, yeah, the lattice structure gives us that set of red points. And
can share it, right?
that's, yeah, the modular transformation into that fundamental domain is what gives us the blue points then, some of which turn out to be these normal rectangular tori, even though they come out as skewed in the lattice construction.
Very good. Keep on going.
Keep on going. So get back to out of the backup slides and into, yeah, the motivation for looking at the finite temperature behavior of these dimensionally reduced systems. The gauge gravity duality we've been hearing about identifies so imposing thermal boundary conditions relates these super Yang-Mills systems to the presence of a black hole horizon or some black brains in that dual supergravity system. I won't go into any details about that because that's not what I know really. And there's a nice illustration here by my collaborator, Toby, who tells me everything I know about this, showing how in order to get to the leading order supergravity in the near horizon regime, we need to look at low temperatures in the super Yang-Mills system that control alpha prime corrections, as well as a large number of colors that control perturbative string corrections in the string coupling. And I should mention as well, the last thing here is that the temporal extent of this 2 torus gives us a dimensionless temperature, just as its inverse. So the temperature is the inverse extent of the torus in the temporal direction. And that's related to the dimensionful temperature by the square root of this 't Hooft coupling that now has dimension 2 in a 2-dimensional system. So if we look at some of the limits of these torus sizes, RL and R beta, we get a plane like this where there are regimes where we have fairly solid expectations from different origins. At high temperatures, we expect the fermions in this system to pick up a large thermal mass. So the temperature breaks the supersymmetry. If we go to the very high temperature regime, which corresponds to a small R beta, those fermions pick up a large mass, supersymmetry is broken badly. We expect the scalars to decouple as well. We end up with some bosonic quantum mechanics where there's been a nice analysis just a few years ago that probably Georg Bregner will tell you about, showing that there is a first order spatial deconfinement transition as we vary the spatial size of the torus and that high temperature regime. And in the opposite regime of low temperatures, where this holographic duality can be expected to be more reliable, there's also a prediction of a first order transition, dual to Gregory-Laflamme transition, that goes between a D1 phase, where the horizon is extended around one spatial direction at large spatial torus sizes, that transitions to a D0 phase, where that horizon collapses to a localized black hole at smaller spatial lengths. And the order parameter for this transition that we can look at in a lattice calculation is the Wilson line wrapping around the torus in that spatial direction. So we can call this, with some abuse of terminology, a spatial deconfinement transition that looks sort of like this in numerical data, all of which was collected by Rogov.
Can I ask a question?
Yes,
There is no confined phase in this diagram.
that's correct. So thermally, the system is always deconfined to be dual to that black hole.
Okay.
And I meant to mention that, so thanks for reminding me
Okay.
to cover it. So this
so-
spatial deconfinement is different than the thermal deconfinement.
Okay. So and in the gravity dual, alpha corrections were included, or those are without alpha prime corrections?
Without the alpha prime corrections, you want to avoid all the complications of computing anything beyond leading order supergravity.
Okay.
And I say we, I don't do any of the supergravity calculations, but we want to get to that limit where the gravity dual is as simple as possible.
Okay. Yeah, thank you.
So yeah, numerical data, thanks to Regov. Looking at that, the trace of that spatial Wilson line, as well as the corresponding susceptibility, where the transition corresponds to the peaks in these susceptibilities that occur where the trace itself shifts between a large value, that deconfined phase at high temperatures. And I should say that the horizontal axis here, this R beta, is being taken to be proportional
Can I
to
ask
R
one more
sub
question?
L. You
Sorry.
can, yeah.
This phase transition is from that deconfined phase to deconfined phase, right?
So here it's, yeah, thermally deconfined on both sides of the transition.
Okay, so
Yes.
I mean, how these are important? For example, this is kind of transition from deconfined phase to deconfined phase. I mean, what is the importance of this? You know.
So we have basically, maybe I can back up and remind you or tell people that deconfinement as a transition is related to the breaking of a center symmetry in the lattice context.
Okay.
And we have different center symmetries around each of the dimensions available to us, that spatial direction and that time direction.
Okay.
So there are two center symmetries that we can either have preserved or can break. And as we go through this transition, the center symmetry is going to be broken in the thermal direction on both sides.
Okay.
That's the deconfined, that corresponds to the deconfined phase, a broken center symmetry. And then what changes is the center symmetry along the spatial direction changes from being preserved in the spatially confined phase
Okay.
to being broken in that other phase. So in both phases, the thermal center is broken, and then the distinction is what happens to the spatial center symmetry.
Okay. Thanks. Thanks.
So yeah, this is a Wilson line wrapping around the spatial direction. If we were to look at the Wilson line around the temporal direction, it would not show a transition like this. And the reason I'm able to plot this against the inverse temperature is because I fixed the shape of the torus, the ratio of its spatial and temporal extents. So by varying R beta, I am varying the spatial direction along essentially a diagonal line in this plot, or in this this cartoon, this diagram. And because I've taken a large aspect ratio of alpha equals 4 in this plot, I'm actually going, hitting the transition at a fairly high temperature, or a small R beta around 0.2, the temperature itself around 5. And we can see that as the gauge group becomes larger, so SUN with a larger N, the Wilson line in the confined phase at low temperatures gets closer and closer to 0 and will eventually reach 0 in the large N limit, where it becomes a bona fide order parameter. I'm also here comparing a couple of different lattice volumes, not doing any extrapolation, but seeing that the discretization effects coming from the different lattice volumes are not significant here. And if I then take the transition that we're able to read off from those sorts of data, put it on that same phase diagram of R beta on the vertical axis and RL on the horizontal axis, what we were just looking at was the alpha equals 4 diagonal line. So that one there, it's a very nice, sharp, well-defined transition, just starting to deviate from the bosonic quantum mechanics result. And as we go to lower temperatures, the numerical calculations become more challenging, the error bars increase. Roughly, we are seeing consistency with the expectations for both the high and low temperature regimes, but there's obviously room for improvement in the numerical calculations, pushing towards those lower temperatures and the holographic regime. So going to lattice gauge theories with larger numbers of colors should help. The maximum in this study was 16 numbers of colors. And it's also important to control extrapolations to the continuum limit and the large N limit, which is part of what you'll see when I talk about this again on Monday in the 3-dimensional context. So one brief aside, because I'm giving a lecture here, not just going over my own work, though I am sort of highlighting what I know best. Something interesting to consider in 2 dimensions is possibilities for different formulations of these theories. And I'm in particular going to highlight one that was actually the first one to come along, introduced by Sugino close to 20 years ago, which is based on a different twist. So it's still a twisted formulation of super Yang-Mills, looking at a different twist. It's a so-called A-twist that I won't go into any details about. I'll just highlight some of the differences between what we looked at earlier this week. So unlike the so-called B-twist, that is what you've been hearing about from me in the past few lectures, this A-twist doesn't take the step of working with complexified gauge links. It keeps the gauge bosons and the scalars separate in the formulation. It, in particular, keeps the gauge links in the group the way you would for a lattice QCD calculation. So you have SUN gauge invariance. You don't have any of the issues with that U1 sector that we wrestled with yesterday. The downside is that the twisted scalar supersymmetry in this A-twist is no longer exactly nilpotent, but it is a gauge transformation. And if you try to do a numerical calculation with this, you avoid the issues with that U1 sector. Instead, you have issues with these degenerate vacua that, as we discussed in the previous lecture, you don't want to average over lots of degenerate vacua. You have to pick out a proper one, impose a condition. Now, not just when you take the continuum limit, but anytime you try to sample a field configuration in an iteration of a Monte Carlo algorithm. In particular, there is the number of vacua increases exponentially with the lattice volume, eventually becoming infinite in the continuum limit. And in 2 dimensions, but only in 2 dimensions, there was a way found around this obstruction that has enabled some ongoing work that may be interesting to some of the audience that has been looking at formulating this A-twisted super Yang-Mills theory with 4 supercharges. So dimensional reduction of n equal 1 super Yang-Mills as opposed to n equal 4. They are able to formulate this on arbitrary polygon decompositions, so discretizations of Riemann surfaces, so 2-dimensional Riemann surfaces potentially with curvature. This was the first paper where that was proposed and introduced, and this group centered around Somatsura has continued working on that with their most recent work from last November, looking at connections between this formulation and graph theory. So I'll leave those references for you to explore if you're curious about going beyond square lattices on flat space, and instead just someone might be. Just a few highlights about the, even going to the ultimate simplification, compactifying away all the spatial dimensions and just having a quantum mechanical system of n by n matrices interacting with each other as they evolve in Euclidean time at a single spatial point. So these are the matrix models that Georg will tell you lots about next week. I'm not going to try to steal his thunder, but just give you some reason to look forward to what he will be presenting. Some of the best work that's been done in this context, looking at the super Yang-Mills quantum mechanics with 16 supercharges coming from the dimensional reduction of n equal 4 super Yang-Mills, has been to look at the bosonic action of the lattice system that's dual to the internal energy of the holographic black hole that is conjectured to be related to it, and working very carefully with a large number of colors up to 32, a large number of lattice sites also up to 32, taking well-controlled extrapolations in both of those variables to get a set of points that approaches the leading order supergravity prediction for this black hole internal energy in that regime of low temperatures where the alpha prime corrections can be neglected, and also even revealing some of those higher order corrections that are hard to compute on the gravitational side, and looking at what you are able to predict or check about both the functional dependence and the specific coefficients of the expansion and the dependence of this energy on the temperature as you go beyond that leading order limit at higher temperatures. I'll also flash a bit of work in progress that I'm doing with Vragov and Anosh, looking at a generalization of that dimensionally reduced super Yang mills. It was due to David with Maldacena and Nastasia, the BMN model that came up in David's lectures briefly, where this is generalizing that quantum mechanical system while still preserving all 16 supercharges, giving effectively another parameter, a supersymmetric mass term that is parameterized by mu, which I forgot to escape in LaTeX, and some more interesting behavior that we can look at in these lattice calculations, in particular phase transitions at some critical value of the ratio of this temperature to that deformation parameter. And again, there are predictions that you can get for this result in various limits, and the weak coupling limit that's been computed to at least NNLO order in perturbation theory. In the strong coupling limit, there is a result, I think it's by Diaz from holography. We might hear a bit about generalizations of that next week. So that's the strong coupling limit at large N. The lattice results that we have so far for 8, 12, and 16 colors, looking at dimensionless couplings that span about 3 orders of magnitude, are in good agreement with the perturbative results at weak couplings and approaching that holographic limit at the strongest couplings we're able to look at with our lattice action before running into discretization lattice artifacts that we're unable to control. So there is a lattice proceedings from earlier this year online, and hopefully the final results, no longer preliminary, to appear in September or as soon as possible thereafter. So that's a quick pass through lower dimensions. Lots of work that I neglected there, but hopefully a bit of context and some interest for you to get inspired to go through that literature if you want. I will now get back to 4 dimensions, look at the case of minimal n=1 super Yang mills, unless there are any questions before I abandon these extended supersymmetric theories, at least for the time being. And there is one coming. So yeah, I put the reference on the slide
I think
rather
I
than.
think I got it now. Yeah. What's the reference? I just missed it.
So it's right there. And if you do an Inspire search for Somatsura and this, so it's even a random geometry, a random triangulation, for instance, of a 2-dimensional Riemann surface. And actually, they go beyond triangulations and look at any polygons. So in this formulation, they have the same sort of geometric Kähler-Dirac fermions in 2 dimensions that we were looking at. So site, link, and face variables, and a prescription for associating these site, link, and face fermions to the vertices, edges, and faces of these polygons that they use to discretize the Riemann surface. Any further questions while that picture is being taken? Just for the recording, yeah. I think it does turn itself off. It doesn't hear anything for a few seconds.
Yeah, I mean, actually, Simon keeps reminding me that random triangulation is uniquely useful in 2 dimensions. It seems to break down in higher dimensions. Yeah.
Yeah, it's lower dimensions are easier. And Simon did some of his earliest work in dynamical triangulations as a formulation of quantum gravity. This is not going there directly. It's still a field theory, and it's also going beyond triangulations, but it is something that is possibly of interest.
But I mean,
in two
random triangulation can solve two-dimensional string theory. Unfortunately, it can't go beyond that. I mean,
Right.
unless something's happened, which I haven't heard about.
I don't think it has.
Okay, good.
Yeah, and this story is only for the deconfined phase, because in that picture there were no confined phase. So how is story will change for the confined phase?
So at least when we're looking at this finite temperature phase diagram, we've only ever considered the deconfined phase because we're motivated by that holographic connection,
Okay.
which is really well defined when you have that black hole corresponding to the deconfined phase. And so I know in 4 dimensions where I tend to live, the 16 supercharged theory is always deconfined. That was the sanity check for the static potential, that it always has this Coulomb potential form. Whether that changes in 2 dimensions and there are confined phases that are interesting to look at is something I don't even know.
Yeah, I guess in supergravity side we can look at by thermal background below TC, deconfinement temperature.
So that may be worth discussing, just you and I
Yeah.
later in this program.
And
could
one more thing,
motivate.
this is the size of the torus which is controlling the transition here. For example, in this graph, like GL transition, deconfinement transition. So it is the size of the torus which is the parameter which is controlling the transition on the gravity dual side.
So
Tori,
yeah, really the shape of the torus rather than its size
okay,
that matters, because we have gone along, we did our investigation by scanning these diagonal dashed lines of fixed shape changing the size, but you can also just as well fix this temperature and scan just in R sub L.
yeah,
And that is maybe more natural to think about in
okay,
a continuum context as opposed to a lattice calculation. So there, that fixed temperature is a fixed length of one cycle around the torus.
mhm,
And then what's changing is the shape of the other cycle.
okay,
It's becoming larger or smaller. And that's the most direct way to think about crossing that transition. It's just not the most convenient in a lattice calculation, where we are constrained by having to have an integer number of lattice points along each of those cycles. So it becomes easier to fix the ratio rather than trying to get nice common denominators.
okay, thank you.
Yeah, I just recently learned about Karsh coefficients, where they get around that, how that done.
The only Karsh coefficients that come to mind are the coming from the latent heat and the non-perturbed, the
Right.
anisotropy.
Right.
If you
So
have an
again,
anisotropy
it'll turn out, I'll give you one
lattice
special
spacing.
case where you analytically can go take the derivatives.
Yeah, so that
And maybe you could,
sounds like imposing anisotropic lattice spacings.
that's right. The question is,
Right.
can you solve the problem in that limit? In the ICM model, I'll show you, it's actually known solution. And then Karsh does it by doing a calculation of that asymmetry
Mhm.
so that he can then take derivatives of it. I mean, it is a
Yeah.
method. It's not easy, but it solves a problem. They need that for
That's
finite
what I was
temperature.
about to say, yeah. So that's some of Karsh's work from the mid-90s, I think, was introducing that.
It's absolutely necessary for finite temperature QCD, or you wouldn't be able to.
But as you said, it introduces a complication, which we don't really need to go to. We do just as well fixing the size and scanning along these
No, I
diagrams.
wasn't recommending it. I'm just saying there is another approach. Yeah.
There are ways to do things that are more complicated, and if we need to, they're available. We don't need to yet. Further questions about lower dimensions before I move on? Okay, so really I personally have not worked on N=1 super Yang-Mills, but for many years it was a main focus of the lattice supersymmetry community. Especially before the LHC came online, they were motivated by the possibility of supersymmetric extensions of the standard model, which would be at least one sector of that would be N=1 super QCD. systems, and N=1 super Yang Mills is then a first step towards that. So there's been a lot of work over many years, and this benefits from a great deal of simplification just by the fact that with minimal supersymmetry, we don't have any of the scalars to introduce these SUSY violating operators that would have to be fine-tuned away in that lattice calculation, getting back to the starting point for these lectures. So there's no scalar masses, no Yukawa couplings, no 4 scalar quartic terms, also no quarks. There's just that gluino among the fermions. And in fact, if we do a naive discretization like QCD, break that supersymmetry entirely, there turns out to be only one supersymmetry violating operator we have to worry about, exactly that gluino mass. So that's in principle, this gluino mass can be controlled by working with a formulation of lattice fermions that obeys a chiral symmetry. This is something that Anna alluded to in her lectures, the Nielsen-Ninomiya no-go theorem. And the fact that straightforward lattice fermion formulations, the Wilson fermions and staggered fermions that Anna told us about, those explicitly break chiral symmetry, and this gluino mass, as a consequence, picks up a large renormalization that has to be fine-tuned. And people struggled with that fine-tuning for approximately 20 years, from the mid-90s up until about 7 years ago. The alternative of using a more elegant lattice fermion formulations that I'll say just a bit about is that those obey a chiral symmetry on the lattice, but introduce a great deal of computational cost. So there are 2 possibilities that people can and have looked at, either fine-tuning that gluino mass and trying to restore supersymmetry in the chiral continuum limit, so a simultaneous extrapolation to vanishing lattice spacing and vanishing gluino mass, or working with those numerically expensive overlap or domain wall fermions. Supersymmetry is automatically recovered as an accidental symmetry if we just take that continuum limit. We don't have to worry about fine-tuning a large gluino mass additive renormalization. Now, most of the recent work has just gone with the simple discretization using Wilson fermions like Anna has told us about, and fine-tuning that gluino mass. So I'll flash a few highlights from this line of work from the community over the past few years. One of the main targets that people involved in this work have been looking for since the mid-90s has been to see the formation of supersymmetry multiplets in this chiral continuum limit, which are predicted that the composite particles, scalar, pseudoscalar, and a fermion gluino glue particle with the gluino and the adjoint representation are predicted to form a degenerate multiplet in that massless limit. And just in the past few years, this has been seen very robustly by this collaboration that includes Georg Bergner, who will be here shortly. So these are the 3 states that are predicted to form this multiplet. And as the lattice spacing gets finer, closer to the continuum limit, that multiplet formation in the 0 mass limit becomes better. Looks like there's a question about
Yes.
this.
In N=1 QCD, super QCD, there's n vacua.
Mhm.
Do people see the domain walls between them?
So that's super QCD rather than super Yang Mills. So it's in super Yang Mills as well.
Well, there's n vacua, that's the within it.
Mhm.
So
Yeah.
There are n vacua in super Yang Mills in N=1 in 4 dimensions. So do they see the domain walls between the vacua?
That has not been seen yet. And to my knowledge, the only fellow who has tried to look at this is Mike Tepper about 25 years ago, without success. And I know this because there's a fellow in Illinois, or two fellows, Patrick Draper and Newman Butt. Newman was a former PhD student of Simon Catterall's at Syracuse, now a postdoc in Urbana-Champaign. They have interest in this, and have talked with Georg and I about whether it might be possible to see. And the answer is maybe we'll investigate, we'll think about it and see what we can do in the future. So that's a nice question looking ahead to sort of work, not yet in progress, but in the air.
Well, the thing is, if you work in this formulation with the mass of the fermions, right, you prefer one vacuum over the other one. So it would be, so you might have completely removed the bubbling that you would.
Sorry, how would you see? Isn't this just the model that Joe Geet ran in domain well fermions?
Yeah, that's coming up in the next slide.
Yeah. So, I mean, it's not that hard, but what do you have to do? You have to change the way you approach the math.
We need another.
The domain wall order parameter, sorry, the vacuum order parameter is the Gluino condensate. So the Gluino condensate needs to have one value, one patch, and a different value.
I think that battery is gone.
But you need to get this mixed.
So when you have many vacua,
Yeah.
you don't cool off to the true vacuum everywhere. Usually you cool off to something where you have domains of the different vacua.
So maybe what I can do is save this for the discussion session
Yes.
in the afternoon, and I'll bring up Mike Tepper's paper, talk about what he tried to do to see this sort of thing. And I think all he says is that it didn't work, and that will clarify what is going on, hopefully. So yes, looking at that continuum limit. So here, these are results for two different lattice spacings. And this group has also been investigating the approach to the continuum limit and seeing how well supersymmetry is restored in terms of ward identity violations like those we talked about yesterday. So computing ward identity violations effectively, I won't go into details about what exactly is plotted on the vertical axis unless there are questions about it, just in the interest of time. They see that an extrapolation to zero lattice spacing, the continuum limit, is consistent with the restoration of that n=1 supersymmetry, and the functional dependence is the expected order A squared for the particular lattice action that they are using. There's also another group taking a different approach to this system, again, working with Wilson type fermions that require a large fine-tuning of the gluino mass, but adding a so-called twisted mass term. This is something that has been productive in lattice QCD. This provides another parameter that can be tuned, ideally to improve the approach to the continuum limit and the behavior of the system at non-zero lattice spacing. So this is just an illustration looking at two different particles, actually unphysical composite states in the system that should be degenerate in that chiral continuum limit against the gluino mass being tuned, and seeing that depending on the twist angle that they incorporate into the calculation, they can get better or worse degeneracy at a finite lattice spacing and non-zero gluino mass. So there is a lot of activity in this way of approaching n=1 super Yang-Mills. And as Rich pointed out, there's an alternative approach, which is working with lattice fermion formulations that exactly preserve some variant of chiral symmetry. And because Anna didn't go into these chiral lattice fermions in her lectures, I wanted to just put up a slide or two about them. There's a really nice story about that Nielsen-Yinomiya no-go theorem. One of the conditions is that this chiral symmetry, the anti-commutation of the Dirac operator with the gamma 5, cannot simultaneously hold if you just have an undoubled local fermion in your lattice spacetime. But way back in 1982, before people were thinking about putting fermions in a numerical calculation, Paul Ginsberg and Ken Wilson noted that even in discrete spacetime, there is a remnant of this anti-commutation relation that can be realized in discrete spacetime. The anti-commutator is equal to d gamma 5d with the factor of the lattice spacing. recovering the continuum chiral symmetry as the lattice spacing goes to 0. And this paper was almost completely ignored for 15 years until Peter Hasenfratz and his brother had to clean his office in Bern and stumbled across it and realized that he was working very hard on a type of lattice fermion that actually obeyed this Ginzburg-Wilson relation. This can be recast as essentially a redefinition of what chiral symmetry means in a discrete spacetime. So instead of anti-commuting with gamma 5, the anti-commutation relation brings in this weird factor of D on either side of the gamma 5. And yeah, it was for many years up until Peter Hasenfratz's serendipitous office cleaning, hard to construct fermion operators that were interacting in a gauge theory that actually obey this Ginzburg-Wilson relation. So one example is so-called overlap operator, which is based on the sign function of a modification of the Wilson fermion operator that Anna did tell us about, which is computationally very difficult to resolve as a matrix function of a very large matrix. So the inverse square root of this matrix squared is something that has to be computed through approximate means up to numerical precision. And it's not that different actually from a so-called domain wall operator that approaches this Ginzburg-Wilson relation by introducing an additional direction to the lattice calculation. So there are the whole four-dimensional gauge theory or the gauge fields are replicated some number of times in this new direction. And this is that work by Rich Brower, Joel Geets, and also Mike Endres, done about 10 years ago to look at n=1 super Yang-Mills, where any bare fermion mass you put in is the coupling between the two different domain walls around which the left and right-handed fermions are localized in this formulation. And then there's a small residual mass coming from the overlap of those fermions as they propagate in that fifth dimension around that midpoint. And as that fifth direction becomes infinitely large, the chiral symmetry becomes exact in that modified sense of the Ginzburg-Wilson relation at non-zero lattice spacing. There has not been much work using overlap or domain wall fermions since 2009. Just about the only publication was this one by Georg Bergner, Stefano Piemonte, and Camilo Lopez a couple of years ago, which was looking at overlap fermions for n=1 super Yang-Mills, approximating that sign function with an n-order polynomial where the nth order is truncating how well the sign function is resolved, how well the Ginzburg-Wilson relation is satisfied. So extrapolating n to infinity or 1/n to 0 essentially corresponds to the chiral limit in the setup where they are able to compute the Gluino condensate in that limit for, in this case, some 12 to the 4th lattices at a fixed lattice spacing with only multiplicative renormalization for both this condensate and the, for this condensate itself as well as other observables. So let's see, I've got about 10 minutes left to talk about super QCD and sign problems. And it looks like there is a question about n=1 before I move on to that. Yeah, this is going to be SU2, I believe, for this is the order of the polynomial approximation to the sign function. So yeah, there are often too many n's floating around, both n=1, n=2 for the gauge group, and then n for the polynomial order. Any further questions? There it is.
The Ginzburg-Wilson paper wasn't ignored just because it was ignored. They did it for the free theory, and they immediately said in the paper, probably this does not work in general for the interacting theory. So they
Even
actually
Ginzburg-Wilson
not
were
only,
able to come up with
they came up with an
solutions.
idea and they killed it, okay? And so that's the reason it was ignored. So don't believe everything that you read in the paper.
yeah, that is a nice addition to that. And looking at the time, I will move ahead to talking about Super QCD and sign problems at least briefly. And there may well be more to say at the end of the day, but I should be able to sort of flash through, but I have just a superficial glimpse at some of these future frontiers for work in this field in the remaining, well, 7 or 8 minutes. So if we take that n=1 super Yang-Mills and we add matter multiplets, quarks and squarks, which could be in some arbitrary representation of the gauge group, well, then the full fine-tuning challenge is back and just as bad as it ever was at the start. And we have, even if we use those overlapper domain wall fermions to control things like the gluino mass and the quark mass, and even help with the Yukawa couplings, we still end up with another 10 or more parameters to try to fine tune, which no one has attempted to do, and well, yet. But there is a lot of interest in trying to push to this. This is where we have those nice electric magnetic dualities, Seiberg duality, the conformal window for super QCD with a known extent, as well as the possibility of investigating some dynamical supersymmetry breaking in the lattice context. And some of the things that folks have been working on in the past few years to try to build up capabilities and machinery to tackle this fine-tuning challenge is even looking at the more complicated lattice perturbation theory calculations, now with all of these quarks and squarks running around the loops, using that as some guide for what that fine-tuning should look at. If the perturbative calculation can tell you a first approximation for the parameters to fine-tune, that could be the difference between something being impractical and something being just realizable with the computing resources that exist, or nearly so. This is, I'll skip the pictures that are some perturbative results for the squark potential from different ways of perturbatively improving or not that setup from Bjorn Velligehausen shared these with me a few years ago. Another way of approaching this that Georg Bergner has worked on is to look at, take a super QCD system, remove the scalars, and then you're left with a more tractable gauge fermion theory that just has fermions transforming in both the adjoint representation and, in this case, the fundamental representation. So quarks and gluinos both present in the system. You can investigate that theory, gain some knowledge about how the lattice calculations behave, what the relevant parameter space is, and that itself could be a launching point for the greater challenge of super QCD in the future. What I've been doing in this area is actually getting back to something simpler and reimposing the twisted approach, the benefits of that. Something fairly remarkable is that the twisted super Yang-Mills theory can be generalized to enable a quiver construction of super QCD theories in 2 or 3 dimensions. This was something initially proposed by So Matsuura and Fumihiko Sugino several years ago now. There's only been one numerical exploration of it so far by Simon Catterall and Arti Virnala. The idea is that you can generalize the twisted theory to have different gauge groups at different lattice sites. And then the field variables, the fermions and the gauge links that connect those different sites now transform in the bifundamental representation of UN and UF rather than the adjoint. And if you take that setup, specialize to a system where you have two-dimensional slices, one with the gauge group fixed to UN, another with that gauge group fixed to UF, you have N times F bifundamental fields connecting them. If you then decouple or freeze the UF slice of this system, make it non-dynamical, what you end up with, looking just at the UN slice, is a UN gauge theory coupled to fields that transform in the fundamental representation of UN with a global UNF flavor symmetry. And because thanks to the twisted construction, you have both the quarks and the squarks associated with these links, bifundamental links. So you end up with super QCD with F hypermultiplets in the fundamental representation by this construction. Now, this paper from 2015 just did some very basic calculations as a proof of principle, looking at both 2-color super QCD with 3 hypermultiplets and 3-color QCD with 2 hypermultiplets, and checking that they behave qualitatively differently in alignment with expectations for dynamical supersymmetry breaking. So I'll skip the story, but there's an expectation that supersymmetry should break spontaneously only when the number of colors is larger than the number of flavors, essentially. And that's what's being shown in this plot here. This is a 2-point function corresponding to a would-be Goldstino. And when the number of flavors is larger, sorry, the number of colors is larger than the number of flavors, this 2-point function decays slowly on log axes. The slope of that line corresponds to the mass of the Goldstino, which is fairly light, corresponding to the slow exponential drop-off. In the other regime, where the number of colors is smaller than F, there's very large drop-off, which means that this state is some lattice dirt living at the cutoff scale. And if you vary the extent of the lattice, you can do a quick extrapolation to a continuum limit, finding that the light Goldstino mass you get in this case extrapolates to something consistent with 0 in that limit. And I currently have a PhD student, Angel Sherlotov, who's working to parallelize this code setup and go beyond this proof of principle and get some more interesting results from this theory. But I have used up almost all of my time, so I will quickly jump to just a couple-minute look at sign problems. I have actually gone through this basic story yesterday in response to a question: what is a sign problem? It happens when we have important sampling Monte Carlo algorithms that have to interpret this e to the minus action factor as a probability. If the action becomes negative valued or complex, that is no longer directly applicable. That is what's known as the sign problem, and it pops up in several places in lattice supersymmetry. So whenever we have spontaneous supersymmetry breaking, there's a story that the Witten index has to be 0. The Witten index is just the lattice partition function with periodic boundary conditions. The integral over these exponential factors, so adding up lots of exponential factors and getting 0 can only happen if some of them are negative. So that implies a severe sign problem. Given this motivation, there's lots of work on sign problems as well from QCD. So we'll hear a lot more about complex Langevin dynamics, tensor networks, and quantum simulation, all ways to tackle this issue. I'll just wrap up by mentioning that n=4 super Yang-Mills does exhibit a sign problem depending on the 't Hooft coupling on the lattice. So integrating over the fermions, we pick up a Pfaffian in the system. In all of the numerical results I've showed you for lattice n=4 super Yang-Mills, I've done a phase quench calculation, as it's called, just dropped the phase of that Pfaffian, worked with its absolute value, and formally I have to reweight all of the observables by the phase that I have dropped. This is just a sort of trivial mathematical identity, but it causes trouble when this phase factor is consistent with 0 and you try to divide by it. So looking at this phase factor can tell you how severe that sign problem is. If we're at a weak coupling, then this phase is just about 1. This is a logarithmic scale, but showing only per mil level fluctuations going out to the largest lattice volumes where I can compute this Pfaffian, which is thousands of times more expensive than actually doing a rational hybrid Monte Carlo calculation, which is why the sign problem is problematic. So things are well behaved even as the volume increases at weak couplings. But as we go off to stronger couplings, then this phase factor starts crashing down to zero, at least with this improved action I'm considering here. And some of that work that's ongoing by Simon Catterall and Göksu Toga that I mentioned yesterday is looking to see if this can be avoided by being more clever with the lattice action that we impose. So I'm over time, I'm in the way of your lunch. We got through every item in the plan, hopefully showing that while there are challenges to lattice supersymmetry, at least some of those have been overcome. And as more are tackled and dealt with, many more opportunities are arising for lattice studies in various different, with various different focuses, from BSM physics to holography and N=4 super Yang mills. So there's a question time. At the end of the day, I'm also happy to take immediate questions now, but there's been a good stream of them through the talk, and it is over time. So just one quick call for any questions before we break for lunch. Looks like there's one in the
So
second row.
is there any work on lattice QCD for actual QCD without supersymmetry?
And what?
Any work from lattice QCD for the actual QCD when there is no symmetry, supersymmetry?
There's a whole field working on lattice QCD and related field
Okay.
theories.
Without supersymmetry.
Yeah.
Okay.
So supersymmetry is sort of a small subgroup of that, percent level effect. So everything I've told you is 1 part in 100 of the lattice gauge theory community.
Okay.
And about 2 weeks ago, there was the annual lattice conference with 420 lattice field theorists getting together in Germany to tell each other about what they've been doing since lockdown.
Okay.
I mean, the QCD effort has become industrial strength. I mean, around the world. In the US, we're about to build exascale machines, okay? And it's huge. And in fact, one of my sort of, if you like, sociological thing, there is this gigantic business of large machines and lattice QCD. And if we could get into that community and use even 5% of what is used in lattice QCD, it would be a huge boost. And we don't have to reinvent it. It's becoming more and more, like, because of big data and machine learning, we used to be a kind of funny group that wanted big machines, but actually the whole climate has changed now. There's gigantic machines being built around the world. So the opportunity is great if you can, and there's also lots of codes. For example, I mean, domain well codes are fantastically well optimized now, and they're easy to use. You can basically use them. So I think there are opportunities. Of course, it always takes work to use somebody else's system, but the growth in power and the size of this community is amazing. I mean, it's like the LHC of theory, right? And so we should try to figure out how to use it.
I guess for those for whom exascale doesn't have meaning, we could try to put a price tag on it. Some of these machines are probably costing, what, $100 million?
Yeah, well, first of all, exascale is 10 to the 18 floating points a second. But the point is that now ones that are petascale, which are 1,000 times smaller than that, are becoming cheap machines. And those are fantastic, right? So, I mean, it's changed immensely. The entry thing is you have to have good parallel code, and they're all GPU based, okay? So, and you don't want to write those codes. I have friends who write those codes from scratch, but for normal people, myself included, you want to use people who've already done that. But the change in power is amazing. I mean, it really is.
Okay. Thanks.
Not seeing any further questions at the moment. I'll call that lunch. And, be back in the afternoon.